aircraft fire protection system has basically two elements to it: fire detection and fire extinguishing. And what you just heard and are still seeing here is a fire detection system doing exactly what it's supposed to be doing, because the function of a fire detection system is to activate a warning device or devices in case you have a power plant fire, a fire in an engine. And the warning devices you just got here were the bell to get your attention and the light to tell you which engine you had a fire in. Now, let's talk about some different types of fire detection systems that we might have. First of all, in the power section of an engine nacelle, we very typically have rate of temperature rise detectors. So what they're detecting is the rate of temperature rise in that area. And the thermocouple system is a fire detection system that does operate on the rate of temperature rise. What it does is it compares the temperature rise at the active points where fires might occur in the engine to a reference temperature point, the reference temperature point being in an area that will heat up when the rest of the engine does if everything's going normally, but in an area that is not likely to actually have a fire in it. So if the thermocouple system senses that you're having a much more rapid temperature rise in one of these active points than at the reference point, it then says, aha, we've got a fire going on here. Now, another type of fire detection system works with a spot detector sensor. And the way that a spot detector sensor works is it is a bimetallic thermoswitch, that closes when it gets heated to a high temperature. Now, one type of spot detector system, the thin wall spot detector system, uses spot detectors wired in parallel so that you've got two loops between two separate circuits, and the reason for that is so that a short in either circuit will not cause a false fire warning. And that's the thin wall spot detector system, and it uses spot detectors wired in parallel with two circuits. Now, another type of fire detection system is a continuous loop detector. The continuous loop detector is basically what its name implies: continuous loops going around the engine area where there might be a fire. The continuous loop detector not only will sense a fire, but it also is an overheat detector. In other words, rather than just a fire going, if the whole general area overheats and gets too hot, a continuous loop detector will detect that also, whereas a lot of other types of fire detector sensors will not. Now, the basic principle that the continuous loop fire detection system operates on is that you have a core resistance material which prevents current from moving at normal temperature, but at higher temperature it lets the current flow. And there's basically two types of continuous loop system: the thin wall and the KID. The thin wall continuous loop system uses a single wire surrounded by a continuous string of ceramic beads in a tube. On the other hand, the KID fire detection system, continuous loop system, uses two wires that are embedded in a ceramic core within a tube. Now, you're going to need to know for the test which one of these, the thin wall or the KID, uses one wire and which one uses two. And here's the way that I use to remember it. I look at the word KID and it's got a double D. It's got two D's in the middle of it. So the KID fire detection system has two wires in the middle of it. The KID system has two wires just like it has two D's, and the thin wall system only has one wire. Now notice that there are two different types of thin wall systems, and that can get confusing on the test. Here you're looking at a thin wall continuous loop system with a single wire in the middle of a tube, and just a minute ago we talked about the thin wall spot detector where you've got it wired up with two different circuits. So don't get those confused on the test. Now, another type of fire detection system is the Lindbergh continuous element system. And the Lindbergh continuous element system operates on the principle of gas pressure within a tube being proportional to temperature. And what that basically means is, as long as the temperature is normal where the sensing element is located, the gas stays entrapped inside this gas-releasing element in the middle. But when you start heating that up, the element in the middle starts releasing gas, and that builds up gas pressure, and what that does eventually is it will close a switch, and that will set off a fire warning or an overheat light. So the Lindbergh continuous element system operates on the principle of gas pressure increasing as the temperature increases. Now, a very similar type system with a different name is a Cistron-Donner fire detector. The Cistron-Donner fire detector is very, very similar to the Lindbergh system, meaning basically that it releases gas and builds up pressure as the element heats up. In both of these, but they're going to ask you about it on the Cistron-Donner fire detector, the detection system will automatically reset when the fire is extinguished or the overheat condition is removed. And that's just a fancy way of saying that when the element cools down, the gas is reabsorbed into the center element, and that will release the pressure and turn off the switch and reset the system so it can respond to a new fire or a new overheat condition. Now, when you're working with reciprocating engines, one thing that you do not use is smoke detectors to detect fire in a reciprocating engine. Lots of other types of sensors, but you do not use smoke detectors to check for fires in a reciprocating engine. Let's talk now about testing the fire detection system. On both the thermocouple system and the Lindbergh system, if you're going to test those systems, you use heat in the normal testing of the system. In other words, you actually use heat to heat up the system in both the thermocouple and the Lindbergh system and see if everything works properly. You're not just checking an electric circuit, you're actually heating the system to see if it's going to work properly. Now, in regard to continuous loop systems, the Finwall system and the KID system, continuous loop systems, both of those type of systems, and this is one of the advantages of them, will still detect a fire if an element is inoperative. An inoperative element means that you've got a broken wire somewhere. They will still detect a fire even if you've got a broken wire, even if you've got an element inoperative. What they will not do if they've got an inoperative element is they will not test when the test circuit is energized. So if you go and energize the test circuit and you don't get a good test indication, it means that you've got a broken wire or an inoperative element in the Finwall or the KID system. But they will still let you know, even in spite of that broken wire or element, if you get a fire. Now, let's talk about fire extinguishing systems. If you've got a fire and up in the cockpit you pull that engine fire handle, what does pulling that engine fire handle do? Well, pulling the engine fire handle closes the fuel shutoff, it closes the hydraulic shutoff, it disconnects the generator from the electrical system, and it also arms the fire extinguishing system. So it does a lot of things to clean up that engine and get it ready to handle a fire. Closes the fuel shutoff, closes the hydraulic shutoff, disconnects the generator, and it also arms the fire extinguishing system, which is the fire bottles that have the agent to put out the fire in that engine. Now let's take a close-up look at the fire extinguishing system, at the fire bottles, and talk about how they work. In the fire bottle, particularly if you have a high rate of discharge, and they abbreviate that HRD container, you're going to have two discs that hold the charge in the container. You've got a nitrogen charge and a fire extinguishing agent combined in that container, and you've got both a breakable disc and you've got a fusible disc. Now, the fusible disc is there as basically an escape in case you have a thermal discharge. And what that means is a thermal discharge means that that bottle has overheated and overpressurized, and rather than blowing up and scattering pieces all over the airplane, what it does is it blows out this fusible disc here and escapes out of the bottle that way, so it's kind of a controlled emergency relief valve in case of thermal discharge. The breakable disc is what is used in the event of a normal discharge meaning an intentional discharge into an engine to put out an engine fire. And with that, what you have is an electrically discharged cartridge down here. And when you hit the button for that particular fire bottle, what you're doing is firing that cartridge, which will then break this breakable disc, and that will release the nitrogen charge and the fire extinguishing agent into the tubing, which then carries it into the engine. Now, that explosive cartridge, you should know, is a life-dated unit. In other words, it's got a definite lifetime to it, because you want to make sure that when you need it, it is going to fire as it should. And so it has to be replaced from time to time, and that varies with the type of cartridge. Now let's take a look at what happens on the outside of the airplane when we discharge the fire bottles. In a fixed fire extinguishing system, there will be a couple of small lines running through from the system which go through ports, and they're covered with a yellow blowout disc. That yellow blowout disc gets punched out by the pressure when you discharge the fire extinguishing bottle into an engine. So when you're doing a walk around the airplane and you look at the disc, if the yellow blowout disc is missing, it means that the fire bottle has been discharged intentionally into an engine. Now, if they have thermally discharged, in other words, overpressurized and gone through that fusible disc in order to give a release to the bottle in a kind of emergency valve situation, there are red blowout discs for that. So if the FAA said to you on the test, the fire bottles have been discharged normally into the engine, and then they ask you what color blowout disc would be missing, would it be yellow or red for a normal discharge into an engine? Yellow for a normal discharge into an engine, and if the red disc is missing, it means that there's been what kind of discharge? A thermal discharge because of an overpressurization in the bottle. Now, there are maximum and minimum limits that these bottles can have. So take a look at your King course book in the back of it at Appendix 2 and take a look at Figure 2. And notice that for the container pressure versus temperature, the left-hand column here gives us temperatures in degrees Fahrenheit, and the two right-hand columns tell us what the container pressure can be, the minimum container pressure and the maximum container pressure. That's in pounds per square inch on the gauge, on the container gauge, and there is a minimum and a maximum that container pressure can be depending on what the Fahrenheit temperature is. And if the container pressure is not within those limits, then it's going to have to be replaced. Okay, so what's the FAA tell you on the test? They tell you that the temperature is 75 degrees Fahrenheit, and they want to know the minimum and maximum container pressure limits. So take a look down the left-hand column, which is for temperature, and son of a gun, as you get towards the bottom, you'll find that we've got a temperature of 70 degrees and a temperature of 80 degrees, but we don't have one for 75 degrees, so we're going to have to do some interpolation. Now, 75 degrees is exactly halfway between 70 and 80, so that's going to help out a little bit when we do our interpolation. Let's take a look now to the right at the middle column in the table, and that's the column for the minimum container pressure at that temperature. And notice that at 70 degrees, the minimum pressure is 319 psi, and at 80 degrees, the minimum pressure is 356 psi. let's take a look at how those numbers work out when we do our interpolation. We had 319 and 356, and if we add them together and divide by 2, that will give us the required minimum pressure exactly halfway between them. 319 plus 356 is 675. Divide by 2 to get exactly halfway between, and that's 337.5 psig, or pounds per square inch on the gauge. And the closest answer you'll find is 338. 338. Okay, that gives us our minimum pressure, but how about our maximum pressure? And looking at the table again, this time we look in the far right-hand column, and at a temperature of 70 degrees, the maximum pressure would be 405. At a temperature of 80 degrees, the maximum pressure is 443. So let's take a look at how those numbers work out for the interpolation. 405 plus 443 is 848. Divide by 2 to get exactly halfway between them, and the maximum container pressure is 424 psig at our temperature. So at 75 degrees Fahrenheit, our minimum pressure was 338, and our maximum pressure was 424. Now, sometimes they have you use a graph instead of a table. Take a look now at figure 3. Basically what we have is up the left-hand side, which we're going to look at in a minute, is the pressure that we're going for. Across the bottom is the temperature in degrees Fahrenheit, cold on the left side, getting warmer as we move to the right. And we've got two lines on there, the bottom line for the minimum gauge reading, these diagonal lines sloping up to the right, and the line above it is for the maximum gauge reading. Okay, this time they say that the temperature is 50 degrees Fahrenheit. So what you want to do is come across the bottom until you find a temperature of 50 degrees Fahrenheit. And when you get to the 50 degree Fahrenheit point, go right straight up that line. Now we're going to find the minimum pressure allowed first, so go right straight up that line until you hit the diagonal sloping line, the first one, which is for the minimum pressure we're allowed. And when you hit that, stop and put a dot. Once you've done that, now you're ready to transfer that dot all the way over to the left-hand side of the graph. Straight line all the way over. Now when you get to the left-hand side, notice that the numbered line below us is for 400 psi. The numbered line above us is for 500. There is an unnumbered line between. So we have a difference of 100 psi here, and we've got 2 blocks, and that means that each one of these blocks is worth 50 psi. So the numbered line here is 400. The one above it that is not labeled is 450 psi, and the one above that is 500. So looking at where our line comes across, it looks that we're like our minimum pressure that we're allowed at 50 degrees Fahrenheit is going to be about 475 psig, pounds per square inch on the gauge, 475. Okay, that takes care of the minimum gauge reading, but how about the maximum gauge reading? For the maximum gauge reading, we go to the bottom again to a temperature of 50 degrees. And we go right straight up the 50 degree line. This time we're going to the top line because the top diagonal line is the one for the maximum pressure. And when we get to that top diagonal line, stop and make a dot. And then simply transfer that dot straight on across to the left. And you get all the way over to the left-hand side. The line just below us is labeled 600 psi. There's an unlabeled line above us, and the line above that is 700 psi. So the unlabeled line above us is 650 psi. And we're halfway between the line for 600 and the unlabeled line for 650. So it looks like about 625 psi. On this graph, at a temperature of 50 degrees Fahrenheit, the minimum gauge reading is 475 psig, and the maximum gauge reading is 625 PSIG. Okay, we fired off the fire bottle. How do we spread all of that stuff around in the engine? The way you spread it around in the engine is by using spray nozzles and perforated tubing to distribute the fire extinguishing agent into the engine section. Dump it all out in the engine section so it can put out that fire. If you get a fire in the induction system when you're starting an aircraft engine, what do you want to do? Well, in that case, you want to continue cranking the engine because you're going to have a lot more problems if you quit cranking than if you keep cranking with a fire in the induction system. Now, by the way, aircraft power plant areas are divided into fire zones, and the way they're divided into fire zones is based on the volume and smoothness of the airflow through the engine compartments, because the more volume of air and depending on the types of obstructions in the engine compartments, the more problems you're going to have with fires. Talking about fires, let's talk about different types of aircraft fires. First of all, a gasoline or oil fire is defined as a Class B fire. And you need to know, by the way, these definitions on different classes of fires. Gasoline or oil fire is a Class B fire. Now, what about an electrical fire? An electrical fire is a Class C fire. So if they said to you that you had a fire that involved energized electrical equipment, what class fire would that be? That's right, that's a Class C fire. Now, another class fire is inflammable metal. Certain metals like magnesium will burn, and a fire in flammable metal is a Class D fire. Now, let's talk about some different types of fire extinguishing agents. First of all, never ever use water on a Class D fire, because a Class D fire, and remember that's a fire in what? A fire in flammable metal like magnesium. If you use water on it, it's going to cause the fire to burn more violently, not less, and it can cause explosions, and it makes the metal splatter, and you've really got problems if you use water on a Class D fire. So in general, we do not use water as an extinguishing agent around airplanes. What do we use then? Carbon dioxide. Carbon dioxide is the most satisfactory agent for an electrical fire as well as for a carburetor or intake fire. Now, how does the carbon dioxide put that fire out? Well, when you use a carbon dioxide extinguisher and the liquid comes out and comes in contact with the air, it converts into snow and gas, and that smothers the flames basically by displacing the oxygen. It does not blow the fire out, and it does not lower the temperature to where it cannot burn anymore. It smothers the flames with the gas. Now, in regard to agents, Halon 1301 is the safest fire extinguishing agent to use from the standpoint of toxicity and corrosion hazards, particularly as opposed to other types of halons. Now, you're going to have to pick out from a list of halon types on the test which one is going to be the safest, and they're going to give you a list of halon 1011, 1202, 1211, and 1301, and they're going to ask you which one of those is the safest. And they're not only going to give you the numbers, they're going to give you the fancy long names. And Halon 1301, get ready for this, is also known as bromotrifluoromethane. But the way I remember that is when they give you the list of the halon agents and ask you which one is the safest for toxicity and corrosion hazards, pick the highest number. The highest number is the 1301, and so the Halon 1301, the highest number in the list you're going to get, is the safest halon fire extinguishing agent to use.